Hi, just wanted to take two videos to approach the idea of graphing rational equations. So I decided I would break it into two pieces because I thought I would do the first two where we had horizontal asymptotes that are in behavior asymptotes, and two where they were not exactly horizontal asymptotes, either a slanted asymptote or maybe a parabolic asymptote. So anyway, let's just kind of see what happens when we attack a couple of questions. So my first one that I have right here is g of x, and what you're going to notice right away in my question is that I have a problem where the degree of the numerator is 2 and the degree of the denominator is 3. So clearly the denominator is a larger power than the numerator. Now I factored this for you, and we did talk about how to go about factoring in our previous unit. Remember all of the numbers that could go into 14 were 1, 2, and 14. The numbers that go into 2 are 1 and 2. We talked about how to do that, but I don't think I would ever ask you to do something that robust on a test to not only graph a rational equation, but also factor it. Usually they'd be given to you in factored form or be more like the numerator where it was fairly simple to get that information. So we're just going to take our way through this a little bit at a time and go grab some easy values. Now, the first thing that I notice is that as you go to either positive or negative infinity, it's going to go to 0. And that comes from the fact that the powers of the numerator and the denominator are different, and the bottom is a larger power. So we know that this graph is going to go to 0 here on the sides. Now, what I don't know is if it's going to come from the high side, come down on that, or the other way. But there's a number of other things that I can grab. For example, I know that there is a root at this problem at negative 1, 2, 3. See, that's where the numerator would go to 0. There's also a root at the number 2, so I have that value. One last little piece that I have, so maybe I could even write that right underneath here. Say negative 3 gives me 0 and 2 gives me 0. Those roots are fairly nice, easy values to get. I also could see that if I plugged in 0 to g itself, g of 0 itself would give me negative 6 over negative 14, which is 3/7. So right here, if I plug in 0, I've got 3/7. And I'm afraid that if I don't put that nice and small, I'm going to end up having something in the way. But that's kind of what I have so far. Now, I also know that based on where the denominator goes to 0, we have a few vertical asymptotes. So I see that there's a vertical asymptote right here at negative 1. So I'm going to go ahead and graph a vertical asymptote at negative 1. I also see that there's a vertical asymptote at negative 7/2, which is negative 3.5, right in here somewhere. And this last part that I wanted to hit with you guys was that right now we have some kind of a problem specifically at the number 2. And there's a hole at 2, but we're going to have to decide where that hole is in a second. Oh, and I accidentally put that on here, didn't I? So it does not have a root at 2, 0. There's a hole there. So we're going to figure what that is here in just a second. Forgot I had that down. So the first thing that I want to do is I want to decide what is going to happen when I get close over here to negative 7/2 from the left, and what happens as I get close to negative 7/2 from the right. Now, what I personally like to do is I like to think of a number like negative 3.6. And then I go through each of the pieces and think what would happen if I plugged in something like negative 3.6. This piece would be negative, as would this. Negative 3.6 plus 3, negative 3.6 minus 2. Those are both negative numbers. Negative 3.6 minus 2 is a negative number. Negative 3.6 plus 1 is a negative number. And two negative 3.6s is negative 7.2. Wow, that's a lot of negatives. So that's 1, 2, 3, 4, 5 negatives. So I've got an entire value of negative infinity right here. So the graph is definitely going down, getting close to this asymptote down here. And so What I know right now is the graph is going to kind of come up like this and get close to both of these asymptotes. Fairly simple little idea. Now, when I go over to the next piece, all of these other pieces are going to remain the same. When I go to negative 3.4, let's say, because that's close to 3.5, the other four values are going to stay negative as they were because I haven't moved very much. But at negative 3.4, this one particular piece would become a positive. And if you put all those together, since there's four negatives, I have a positive infinity, so it's going to go up here. Now, that automatically leads me to an idea that this is probably going to be some kind of an S curve, because if it came down here, it can't come through and go back up because there'd be another root, or maybe it would come down and barely touch and go back up. But if it did touch and go back up, that value should be squared. So I'm quite confident it's going to come through like a little S curve based on the fact that there's literally only one root at that. But we're going to double check that regardless. So let's see what happens as I get close to negative 1 from the left side. So if I tried negative 1.1, this value would be positive. Negative 1.1 plus 3. Negative 1.1 minus 2 is also going to be then a negative. Sorry, that was a positive. Negative 1.1 times 2 plus 7 is a positive. Negative 1.1 plus 1 is a negative. And negative 1.1 minus 2 is a negative. So again, I'm just looking at each one of those pieces and imagining what happens if I'm just a little bit below the number negative 1. And I got a positive, a negative, a positive, and 2 negatives, which is a total of 3 negatives. So on the left side of negative 1, right here, it is going down as I predicted. Now, the last thing is, based on seeing this dot right here, I can see immediately it can't come from below and hit it because it would have another root. So it's going to have to come from above, and it's going to have to hit this value and continue on and get close to the origin. But we'll double check that regardless. So let's come in on negative 1 from the high side. So at negative 0.9, I have a positive and a negative. Again, negative 0.9 minus 2 would be negative 2.9. Negative 0.9 times 2 is negative 1.8 plus 7. That's also positive. Negative 0.9 plus 1 is a positive, and negative 0.9 minus 2 is a negative. And so when I put all that together, I have only 2 negatives left, which makes a positive. So it in fact did go to positive infinity here, as I thought. Now, the last part that's a little bit weird, and this is one of the reasons I chose this question, is I wanted to figure out what happens when I get close to 2. Now, 2, remember, is our removable discontinuity that I highlighted here. So if we thought about this, if we just covered those two things up, because again, those two things cover, they really cancel out for every number except at 2 itself, because a number divided by itself should be 1. So they kind of cancel out. But the only number that it doesn't do that to is exactly the number 0. 0 divided by 0 doesn't cancel out. So what I have to think about is what is happening to the other values. So if I plugged in 2 or something super close to 2, then something super close to 2 to 3 is something very, very close to the number 5. And it doesn't matter which side. If I'm very close to 2 and I add 3 to it, I'm very close to 5. Now down here, if I'm very close to 2, I get 4 plus 7 or 11. Now not perfectly 11, but very close to it. That's 11, and 2 plus 1 is 3, or very close to 3. So 11 and 3 makes 33. So I'm not saying that these numbers would be identically 5 over 33, but they're infinitely close to 5 over 33 because that's what I plugged in. So over here, that is the location of this removable discontinuity, is 2 at 2 comma 5 over 33. And that is the end of our story. Now, I did think it would be a good idea to go ahead and look at our friend Desmos and put in some of the information that we discussed. So right off the bat, notice I thought that we had a removable discontinuity at 2 comma 5 over 33. And I'm going to put an open circle there. I figured out that I had a vertical asymptote at x equals -7/2. I'll put a dotted there. I also figured out that I had a vertical asymptote at -1. Let's put a dotted right there. I also noted that it went through 0, 3/7, I think is what we said the y-intercept was. And so now and then we also had, I guess I could put a horizontal asymptote at y equals 0, which is a little hard to see because it's right on the axis. Maybe I should make all of these other ones red so they're distinctively different than the actual curve itself. But let's see what happens if we graph this thing, if it actually fits all the little bells and whistles that we were looking at. So let's go ahead and make this, say, black so we can see it a little bit better. And that looks very much like the curve that we had. It does have our removable discontinuity, our correct value here. And I guess I didn't include my root that I had at -3, 0, but I think if we put that in, you'd see that it was there. So it does validate everything, and I would highly encourage you to check your answers a few times as you're going through to validate and make sure that what you've done is correct. Okay, so one more question on that. This is a much, much shorter question than the previous one. I would have to argue a much easier one. So I have a simple equation that is 2x minus 5 over x plus 2. Right off the bat, we know we have matching powers. And so anytime we have matching powers, we know it is simply going to go to a ratio of those leading coefficients. So this is going to have a horizontal asymptote at the number 2. Perfect. Also, there is a vertical asymptote at -2. Now, this is not factorable, so we're done right there at x equals -2. So we just have to decide what is happening as you get close to -2 from either side. Now, clearly, if there's a number around -2, 2 times -2 is -4, minus 5 is around -9. So it doesn't matter if you're close to -2, a little bit above or a little bit below. -9 is very negative, so we're not worried. But at -2.1 plus 2, that would be a negative answer. So the ratio of two negatives is a positive. So that graph is going up here. Also, if you go from the high side of -2, like -1.9 plus 2, that would be a positive. So that one is going down because of the negative. Now, a couple more little things that we usually try to include. For example, if you plugged in 0 for x, you would get -2.5. So we have 0, -5/2, or -2.5 would be my y-intercept. And if we looked at where the numerator went to 0, 2x minus 5 is 0 at x equals 5/2. Now that just so happens to be coincidentally the same answer as I got the other way, which is kind of weird. But over here at 5/2 is what we got. And I think we can tell the graph has to go about like this and therefore like this. So we could probably just throw those numbers in because literally if it cannot cross the x-axis, it can't be over here because it would have to. So I know from the left side of this, it is going to positive infinity and negative infinity, and we're done. Now, I'm done with that question. There's really nothing more for me to do. But there's a typical thing that we ask you to do, and that is to ask, how is this function f related to the 12 basic functions that we had? And as it turns out, f of x is really very highly related to this guy g of x, which is 1 over x, in the following way. Now, what I'm going to do is I'm going to do synthetic division on -2. And this is a very simple one. 2 times -2 is -4. So that gives me -9. Now, normally I would go ahead and throw that away and say, hey, my end behavior asymptote is 2. But we saw that up here. But I want to know, how is this related to this? And so here we go. What we have then is that f of x is the same as, it is 2x minus 5 over x plus 2. But again, if we divided those, we got the number 2. And then we also got a remainder of -9. So I think I want to write it this way. I want to take away 9 over x plus 2, because that's kind of how division works. So if you were to look at what f of x is, it is g of x, but somebody did a couple things. The first thing is this original x that was sitting here, x was replaced by x plus 2. And so we know that that original graph, 1 over x, is sitting like this, was shifted to the left 2. And if you look up here, you can see that that vertical asymptote was in fact shifted to the left 2. Secondly, there was a -9 in front. So that -9 is going to flip the graph over, which you can see it's down and up, but also it was stretched by a factor of 9. That's why it's so far down. It's not very close to the origin here. See, these were really, really close together. These are really spread out because of that. And last but not least, there's a +2. So that +2 has the effect of taking that original horizontal asymptote and moving it up 2 units, which you can see evidence of right here. So again, how they relate is the original function g was multiplied by -9, that's going to stretch it and flip it over, shifted to the left 2, as well as up 2. And that is the end of my little video on looking at graphing rational equations that happen to have horizontal asymptotes. And I will see you back for another one when we have asymptotes that are not horizontal or vertical. I will see you back in class.